Good afternoon and welcome to the Franz Edelman competition. My name's Ann Robinson. I'm the chair of this year's competition. I ask everyone to silence their cell phones and keep any noise to a minimum as we are recording this session. Just as a point of note, every finalist will have 40 minutes to present their position, as well as 10 minutes of questions from the judges. Now join me in welcoming GE with Norfolk Southern.
Good afternoon. I'm Fred Ehlers, Vice President of Information Technology at Norfolk Southern Corporation. Prior to my current role, I was Vice President of Network and Service Management in the Operations Division and was responsible for the implementation of Movement Planner at NS. We are honored to be among the 6 distinguished finalists named for the Inform's most prestigious honor, the Franz Edelman Award. Together with GE, we developed and implemented the Movement Planner algorithm that our dispatchers are using to run our railroad today. At Norfolk Southern, we operate a rail network that covers 20,000 route miles with connections to every major container port on the eastern United States. We have more than 2,100 train starts per day, 65% of which are scheduled and the rest run on an on-demand basis. Over 30% of our trains carry only intermodal trailers and containers. More than half are mixed freight traffic trains carrying different types of rail cars, while the rest are single commodity unit trains that travel directly from origin to destination without any intermediate handlings. In addition, our network handles 70 passenger trains per day. The movement of trains on the rail network are managed in real time by dispatchers working from 10 dispatch centers. Across those 10 dispatch centers, we have 67 dispatch desks. Each dispatcher controls a territory of track and is responsible for the safe and efficient movement of all trains and on-track equipment for that area. Before movement planners, dispatchers manually planned all activities associated with moving train over his or her territory. These include meets and passes between trains traveling on single track with sidings and other activities such as crew and engine changes, inspection, and other scheduled work events. Our dispatchers do a tremendous job of moving trains safely and efficiently over the network, but a dispatcher focuses only on a small territory that he or she controls and does not have a global view of the entire rail network. Therefore, what looks great on one division for one territory could harm overall network efficiency. Moreover, the sheer volume and complexity of those decisions make it extremely difficult, if not impossible, to make even locally optimal decisions. As a result, those suboptimal decisions can cascade through the network, degrading network performance. Together with GE, we developed and implemented Movement Planner that delivers a single efficient plan for dispatching trains across the entire network. The plan determines the best routes on train priority, schedule, opposing traffic, topography constraints, horsepower, train consist makeup, and other scheduled and non-scheduled events. The following short video summarizes the problem that we have addressed and solution developed.
Moving trains across continents is a monumental task. Every day at Norfolk Southern, tens of thousands of routing decisions are made. Resource constraints impact train movements continuously. Dispatchers move trains safely and efficiently in their territories while responding to constantly changing network conditions. Multiply the number of trains by the number of routing decisions, and you'll see how things become very complex very quickly. When 2 trains meet on a single track, the dispatcher makes a decision about which train to keep moving. All relevant information is considered, including whether each train is on schedule, terminal landing and departure tracks, targeted departure times, each crew's remaining hours of service, unscheduled event locations and dwell, and other variables, including horsepower to tonnage ratios and topography. Dispatchers continuously make individual routing decisions in their territories, and they make them expertly. However, they cannot consider all relevant factors for the entire rail network, as it is beyond the limits of human ability. A good decision for one territory may not be optimal for adjacent territories. Tens of thousands of discrete routing decisions create domino effects that cascade through the network every day, resulting in suboptimal network performance. How can we create better efficiencies across the network? The GE Movement Planner uses complex algorithms that consider all factors that dispatchers do, but considers them in every territory over the entire rail network. Movement Planner produces one optimal plan simultaneously for the entire network, updated in real time and responding to constantly changing conditions. Welcome to today's rail operations. Increased velocity, enhanced asset utilization, and improved network performance. Made possible by the GE Norfolk Southern Partnership and the GE Movement Planner.
We have been utilizing this algorithm for auto-routing trains since March of 2012. Our average speed has increased by 2 miles per hour, decreasing our operating costs while significantly improving our schedule adherence and crew expirations. Our trains are now 15 minutes early on average, while they were about 2 hours late before. Crew expirations, or crews meeting their federal hours of service limits, decreased by about 60%. Benefits from increased velocity include savings in capital and operational expenses. We can now move more trains without laying additional track. It costs us $2 million per mile to lay new track. We can run our railroad with fewer locomotives, fewer crews, and maintain our track with less impact. We need 50 fewer locomotives for each mile per hour increase in speed. The higher velocity decreases crew costs. We can now accurately predict estimated time of arrivals, which improves our customer service and enables better crew management. Data shows that the average speed of freight trains in North America is about 20 miles per hour. Increasing that speed by 1 mile per hour results in a $2.5 billion savings in capital and expense. For Norfolk Southern, that number is $200 million per mile per hour. And we can continue to find add-on benefits with Movement Planner. While we started with creating a better dispatch plan, we have built a foundation to enable benefits in other areas. Charlie will speak to these. Now let me turn it over to Srinivas.
Thanks, Fred. Hi, I'm Srinivas Balapragada, Chief Engineer of Software Sciences and Analytics at GE Global Research Center. Computing a movement plan requires a variety of data on train schedules and operating costs, the topology of the rail network, speed restrictions, and track blocks. The planner also requires data on real-time location of trains, crew reports, and any dispatcher inputs. Because the state of the rail network is constantly changing, the runtime of the algorithm should typically be under 2 minutes to enable real-time dispatching. A train graph is a tool for visualizing a movement plan. The topology of the dispatch territory is represented on the x-axis. Time is represented on the y-axis. Each line in the graph shows the locations of a single train at various points in time. The lines with negative slopes represent trains traveling from left to right, and those with positive slopes represent trains traveling in the opposite direction. At meet and pass locations, the waiting train has a zero velocity, and its train line is vertical. For example, the train traveling from right to left waits in the siding near Briar Creek to let 3 trains traveling in the opposite direction to pass it. The graph also shows an infeasibility near Pruitt, which could easily be resolved by placing one of the trains in the siding. The movement planner problem has been well known for a few decades. Many attempts had been made earlier to solve it by academic researchers, OR departments at railroad companies, and third-party software companies. There are many patent applications filed on different methods for solving it. A recent survey paper reviews 128 research articles that were published on this topic. The movement planner problem is a complex optimization problem requiring many decisions. Most of the available techniques attempt to solve small and approximate versions of real-world problems. Generating even a good feasible solution for real-world problems is very difficult. To date, there has been no other successful implementation of a movement planning solution that is capable of automatically dispatching trains at any major railroad, to the best of our knowledge. So there is no other implementation of this solution at any other railroad. A simpler version of the problem can be formulated as a math program using a network flow model. Many variations of this model are available in literature. However, such formulations for even simple approximations of real-world problems result in mixed integer linear programs with millions of integer variables. Those formulations are too large to be solved using existing MIP solvers. Moreover, it is difficult to capture many real-world requirements in such math program formulations. Real-world movement plans must satisfy many constraints. We broadly group them into 4 categories, the first being track-based requirements. Certain sections of track may be blocked for maintenance and other reasons. Speed limits vary by track section. The switches to move trains between tracks may be locked, limiting track changes. These restrictions could be in effect for the entire plan duration or for a shorter time. The planner should meet these requirements when they are in force, but should take advantage of the increased network capacity to maximize the average train speed when they are no longer active. The height, weight, and width restrictions limit certain trains from using some portions of the track. A train may be required to follow a preferred route as much as possible and only take an alternate path if needed. Some sidings may accommodate multiple trains. Placing multiple trains on such sidings may not only increase the average network speed, but may sometimes be essential to produce a good feasible plan. Train requirements also impose many constraints on the optimization problem. Trains should arrive at their destination on schedule. Their priorities must be respected when scheduling meets and passes. Train priorities can be static or dynamic. For example, a train's priority may increase when it is behind schedule or its crew is nearing expiration. Order constraints require that trains arrive at a certain location in a pre-specified order. Key trains are those that carry hazardous materials. They should not be made to wait in sidings. Local trains that shuttle between rail yards and customer locations do not have a published schedule. The algorithm should modify the plan quickly to accommodate for them when they enter the main line from rail yards or customer locations. In addition to meets and passes, the planner should schedule many other types of activities. And we group these requirements under activity management constraints. Crews cannot operate trains beyond 12 hours as per government regulations. The planner should arrive the trains at crew change locations before their respective crews expire. Combo trains are those where two trains meet at a location and then proceed together forward as a single train. The planner should ensure that both trains arrive at the location at around about the same time. A linked train activity happens when a train drops off some cars at a certain location and a second train arrives there to pick them up. The planner should schedule the first train to arrive at the location before the second train. Some trains may not have enough horsepower to get over hills. Helper locomotives are available in such regions to provide additional horsepower. The planner should schedule helper locomotive activities. The planner should also schedule certain station and off-track activities for trains. Trains enter the main line after completing those activities. Sometimes dispatchers may like to schedule some meets and passes at certain locations. The planner should honor such requests. Unplanned events occur frequently on the rail network. Trains can be early or late when entering the main line. There can be changes in speed restrictions and track blocks. Train priorities can change. Some trains may be cancelled due to lack of demand, while new trains may be added in other areas. The planner should quickly generate new plans in real time to react to changing conditions. The algorithm should also generate robust plans. That is, variation between two consecutive plans should be as small as possible for small changes in input. There are multiple objectives that are of interest to the railroad. The average speed of trains should be maximized. This is mainly achieved by minimizing the amount of time that trains spend waiting in sidings for meets, passes, and other activities. High priority trains should have higher speeds than lower priority trains. Crew expirations result in major expenses to the railroad. Trains stopping mid-route due to expired crews can block traffic and decrease network capacity. Additional costs are incurred in transporting relief crews to replace expired crews. The number of crew expirations should ideally be 0. The percentage of meets and passes retained between two consecutive plans is a measure of plan stability and robustness. If there is no significant change in the plan input, the planner output should not change. Trains should not switch between parallel tracks for no reason. The number of switches to alternate tracks should be minimized. Equal value passes are those where trains with lower priorities pass trains with equal or higher priorities. The algorithm should minimize the number of such pass events. We developed an innovative algorithm that intelligently searches the feasible region to obtain a near optimal solution in real time. The algorithm uses a detailed model of the rail network to simulate movement of trains. It then builds schedules for each train in a systematic manner by moving trains from their current locations towards their respective destinations. Many decisions must be made in developing movement plans. They include the path that each train takes from origin to destination and the locations for meets and passes and other activities. Many possible choices are available for these decisions, resulting in a very large search space. We employ a hybrid combination of heuristic methods, local optimization techniques, and backtracking methods to reduce the search space and develop the solution within 2 minutes. Our algorithm is analogous to a branch and bound approach with a beam search branching strategy. It begins by developing a preferred route for each train. A preferred route is the best possible route that a train should take to achieve all its objectives optimally. In addition to the preferred route, many alternate routes are generated which bypass sections of the preferred route. The algorithm then incrementally moves trains one at a time for a short duration and repeats this process until the end of the time horizon. The next train to be moved is selected based on a number of criteria, including train priority, the delay that the train has already incurred, the extent to which the train has already been advanced, etc. The selected train is moved until it reaches a decision point. A decision point is a node in the network at which more than one route may be available for a train. Once a train reaches a decision point, and the available options are evaluated, and the best train to move next is selected. The best train could be the best option could be to move the train along the preferred route if that is available. Other alternatives include delaying the train at the current location or choosing an alternate route. During the search process, situations can occur where a train cannot be moved further because of unavailability of track due to one of many reasons. When a train encounters such a situation, the planner resolves it in a systematic manner, using multiple techniques, including backtracking trains to search a different region of the search space, delaying them in their current locations, or moving trains along paths that are alternate to the preferred route. The planner repeats this process until all trains reach their destinations or the end of the time horizon is reached. Though we do not achieve the optimal solution, our algorithm achieves a significant improvement of all the performance metrics that are of interest to the railroad. Randy Markley will now talk about testing and software implementation.
Hello, I'm Randy Markley. I'm a principal software architect for GE Transportation. We thoroughly tested the algorithm for feasibility and performance using many real-world scenarios. We measured the performance of the algorithm for these test cases using the plan-level metrics listed in the second column of the table. These metrics are calculated and recorded for each movement plan created. The metrics are then used to derive the corresponding system-level metrics that you see in the first column. The metrics that we use to measure the algorithm performance corresponds to the algorithm objectives described earlier. The metric unresolved conflicts is used to measure the feasibility of the generated plans. The algorithm resolved all real-world test scenarios well within the allotted runtime. There were significant improvements in all metrics when compared with the observed real-world metrics. Upon successful testing of the algorithm, we installed it in Norfolk Southern in 2008 by integrating it into a solution called the Unified Train Control System, or UTCS. The UTCS system is comprised of the movement planner algorithm and of GE's precision dispatch system. GE has since commercialized the planner portion of UTCS into a product offering for other railroads. The network viewer provides visualization of the network plan to dispatchers for coordinating related operational activities. The network optimizer contains the algorithm developed with Norfolk Southern and the operational rules. Automatic execution of the plan is implemented by the train control system with the autorouter. Autorouter translates the plan into route requests, asking the dispatch system to clear a configurable number of signals automatically in front of the train. In this way, train operations become much more efficient, error-free, and the compliance to the plan is dramatically increased, maximizing the benefits of optimization. Though our implementation at Norfolk Southern uses GE's precision dispatch system, our movement planner system, which includes the planning algorithm and the autorouter, can interface with any third-party dispatching system. We're currently implementing the movement planner at 2 other railroads that use other dispatching systems. Our system continuously collects data on plans developed in their real-time execution. We maintain an offline database with 5 years of data. Using this data, we generate reports that measure the impact of movement planner on key performance indicators of the railroad. We also use this data to generate year-over-year reports on planner effectiveness by division. Charlie Turnipseed from Norfolk Southern will now talk about the usage of the system and benefits to Norfolk Southern.
Thank you, Randy. Hello, I'm Charlie Turnipseed, System Manager of Dispatch Operations at Norfolk Southern. We first implemented Movement Planner in our Georgia division and then gradually rolled it out across our other divisions. The system was initially used to advise our dispatchers, but starting in March of 2012, the algorithm began auto-routing trains in the Georgia division, a 240-mile section of track. Over the next 3 years, we rolled out the auto-routing functionality across the other 10 divisions, and since February of 2015, all divisions have been utilizing the algorithm to auto-route the trains. There were many challenges implementing the algorithm, user acceptance being the highest hurdle, overcoming the old way of doing things. I can speak firsthand to this, starting my career at Norfolk Southern as a train dispatcher. Many of our dispatchers have been dispatching the same territory for years, if not decades, applying the same solutions to the same problems. We utilized extensive classroom and on-the-job instruction to demystify the technology, making it less of a black box. We also instituted the concept of a super user, a local on-site peer who has received additional training and acts as an advocate in addition to an expert. We have also instituted a robust feedback process leveraging the super user's expertise and a battery of operational reports. This allows us to replay the manual interventions made by the dispatchers, showing them how their suboptimal decisions and overrides have impacted the network. And of course, this was driven by our senior management sponsorship of the initiative to make sure the full potential of the technology was realized. Communicating the solution to the dispatcher through the Network Visibility Console, or NVC, is one of the methods we utilize to visualize the plan. Y-axis represents time, X is topography, and every string line being a train's path through time. Our dispatchers do a fantastic job at moving freight and on-track equipment safely and efficiently, but with Movement Planner, they do it even better. Much like a game of chess, making optimal near-term decisions requires looking many moves into the future. With Movement Planner, they can see far beyond human capability and how their local decisions impact our network on a global scale. We have systematically analyzed the data generated by Movement Planner to measure improvement of key metrics at all of our divisions. Our Georgia division has been using Movement Planner to auto-route trains for 5 years now. Last year, we had analyzed 4 years of data from the division to measure the benefits. Our analysis shows that the network performance was consistently better when the algorithm was used to auto-route trains. In the Georgia division, when the system was auto-routing more than 80% of the time, the velocity increased by about 2 miles per hour. Crew expirations decreased by 58%, and trains are now 15 minutes early versus being 2 hours late. And we have observed similar improvements at all of our divisions. We can now accurately estimate times of arrivals within 5 minutes, 2 hours out. This capability not only enables us to share more accurate information with our customers, which is especially important to our time-sensitive intermodal business, but also allows for better crew management. Movement Planner receives crew availability information and can adjust train priorities accordingly. Instead of rushing a train to a terminal area only to wait for the outbound crew, if no crew is available, Movement Planner can automatically pace the train against opposing traffic to arrive just in time. Movement Planner provides many benefits beyond our dispatch centers. One such benefit is a means for us to better plan our on-track maintenance. This plan shows where the windows of opportunity are for scheduling maintenance when no trains are planned to travel on the track sections that will be impacted by the work. Our Chief Operating Officer, Mike Wheeler, has the following testimonial video.
Hello, I am Mike Wheeler, Chief Operating Officer at Norfolk Southern Corporation. We are one of the nation's premier transportation companies, operating in 22 states with a rail network that covers 20,000 route miles with connections to every major container port in the eastern United States, serving more than 74% of the nation's population. We pride ourselves on being the most innovative rail company, pushing the boundaries of what is possible with the integration of operations research and analytics to improve the efficiency of our rail network. It is why we are so proud and honored to be nominated with GE for the prestigious Edelman Award. Together with GE, we developed and implemented Movement Planner to dispatch our trains safely and efficiently across our entire network. We can testify firsthand to the benefits and improvements this pioneering technology has delivered. When it comes to moving trains, staying on schedule and network velocity are paramount. Every mile-per-hour increase in velocity translates into roughly $200 million in capital and operational expense savings. Our dispatchers do a tremendous job managing our networks. But with Movement Planner, they do it even better. Movement Planner is critical in helping them comprehensively understand how routing decisions in one territory impact operations on a network scale. With dramatic improvements to schedule adherence, increases in velocity, and a double-digit percentage reduction of crew expirations, the results speak for themselves. Movement Planner also provides a means for us to better plan our track maintenance, displaying windows of opportunity to lessen the impact to operations while passing on more accurate ETAs to our customers. Norfolk Southern has been a pioneer in using operations research to improve our rail operations. Together with GE, we are honored to be considered for this prestigious Operations Research Award, and I thank the Edelman Committee for this opportunity.
Thank you. I would like now to introduce Gianpaolo.
Hello, I'm Gianpaolo Rigo, Senior Product Manager for Movement Planner product at GE Transportation. To date, the revenues to GE from this product are well over 100 million, most of which is from other projects. GE is currently implementing this product at two major railroads, Burlington North Santa Fe, North America, and Horizon in Australia. GE is also in talks to implement the product at several other railroads across the world. Implementation at these railroads will lead to significant additional revenues. Also, this product has tremendous opportunities to be expanded to adjacent markets and other GE businesses. The success of this product led to a major growth in our digital solution business. There are tremendous opportunities for applying operations research methods to improve railroad operations. Increasing the average speed of trains by 1 mile per hour saves the rail industry in North America $2.5 billion per year in operational and capital expenses. Decreasing the amount of time rail cars spend in yards by 1% saves the railroad industry around $2 billion per year. Decreasing fuel consumption by 1% saves 70 million gallons of fuel, which leads to saving of $140 million. And improving locomotive productivity by 1% saves the industry $800 million a year. We now have products that address all these opportunities. We partnered with Norfolk Southern to develop the Yard Planner system, an algorithm that plans the movement and distribution of rail cars in the yard to minimize their dwell time and better predict train departure. We are in the process of integrating the Movement Planner with it. Movement Planner accurately predicts when trains arrive at rail yards. This information is useful to the Yard Planner to develop better yard management plans. Similarly, Yard Planner forecasts when trains leave rail yards to enter the main line. Movement Planner can use this information to generate better movement plans. We also plan to integrate Movement Planner with our Trip Optimizer. Trip Optimizer automatically drives trains to minimize the amount of fuel consumed. It is currently being used on over 7,000 locomotives, reducing fuel consumption by over 10%. Through integration with Movement Planner, Trip Optimizer can accurately information on future meet and pass locations to better drive the train to further decrease fuel consumption. More recently, we have started developing two other optimization-based products to increase the throughput of intermodal and automotive rail terminals. We now offer a connected suite of solutions to the railroad industry under the brand name Rail Connect 360, a landscape of products to minimize operating costs and maximize throughput. The success of Movement Planner led to these opportunities. It has also given us confidence to deliver on complex optimization and analytics projects in our new digital solutions initiative. We are adapting learnings from our railroad efforts to deliver process improvements in other GE industries, such as aviation, power, and healthcare. GE Movement Planner is the solution that is leading today the transformation of GE in a digital industrial company whose future will be shaped and defined in the emerging Internet of Things world as more than 50 billion things become connected over the next 3 years. Movement Planner is one of the earliest examples that has showed us and our customers the tremendous opportunities that can be realized through operations research for new and better ways to manage our assets. The total anticipated value to GE from Movement Planner and its spin-offs is over $1 billion, while our customer will benefit much more. We now conclude our presentation with a testimonial from Jamie Miller, CEO of GE Transportation.
Hi, I'm Jamie Miller, President and CEO of GE Transportation. We are really honored to be nominated as a finalist for the Edelman Award, along with Norfolk Southern, which is a deep partner of ours and really a customer in this digital journey we're on. You know, the software platform we've developed together, it's called Movement Planner, has really shown us the true power of digital technology to transform a whole industry. Bringing together world-class operations research experts at GE's Global Research Labs and engineers at GE Transportation, we developed software algorithms that today are creating hundreds of millions of dollars in value for our rail customers. Movement Planner enables our customers to move their trains 2 miles per hour faster, all without expending an ounce more of fuel and energy. 2 miles per hour may not seem like much, but to the rail industry, it really means billions. Every mile per hour gained represents about a $2.5 billion savings for the industry. The new lines of sight that Movement Planner is giving all rail fleets just are really incredible. The software essentially creates digital models. In GE, we call them a digital twin of the whole fleet that provide real-time information and insights back to the customer. We've got agreements with 2 other major railroads to implement Movement Planner, and working with Norfolk Southern, we also developed the Yard Planner product, which is a direct Movement Planner spinoff. It's used to optimize and manage rail yards. The analytical methods that we refined when we created Movement Planner together are also being applied by other GE businesses in other industries. So look, in the coming years, the digital transformation of rail alone is going to create productivity gains and savings worth really billions of dollars. But putting it together across all GE industries, the total anticipated value to GE, to Movement Planner project, and to all of the spinoffs is really in the billions of dollars, while our customers and industries benefit even more. Operations research and analytics algorithms are the core enabler of the systems. I congratulate the Movement Planner team from GE and at Norfolk Southern for their success. And I really thank the Edelman Award Committee for the opportunity to showcase their great work. So thank you.
I'll now call Fred again to wrap up the presentation.
Thank you. And finally, Movement Planner represents our first major initiative bringing advanced real-time analytics to frontline operations, the people that are actually running the trains. This is a game changer for us. This is big. Thank you for the opportunity.